All right, this is lesson 5.2 and it's quotients of polynomial functions. Up until this point, we've been looking at reciprocal functions, which take an original polynomial and look at what the graph of the reciprocal might look like. So that's 1 over, say, equation of a line or equation of a parabola. Those are the two most common ones that we've looked at so far. In this lesson, we're going to look at the quotient of two polynomial functions. So that would be defined as if we let our function f of x equal p of x over q of x. So we have one polynomial function on top and one polynomial function on bottom. We have a restriction when we are dividing by polynomials because we can't divide by 1. So our restrictions would be that we can't have any value of x that would make the polynomial in the denominator equal 0. This type of function, this quotient of two polynomial functions, is called a rational function. And the ones that we've looked at so far, reciprocal functions, are technically rational functions because the function f of x equals 1 is a polynomial function with a degree of 0. So therefore, if we're looking at an equation like 1 over x plus 1, we have a rational function as well as a reciprocal function. So a couple of examples. Our first example, f of x, 3x squared minus 1 over x plus 1. The top is a quadratic, the bottom is a line. We have polynomial function on top and bottom, therefore we have a rational function. We have a restriction that the denominator cannot equal negative 1. X cannot be negative 1 because that would make the denominator 0, and when we divide by 0 we have a restriction. Our second example, 1 minus x over x squared, is also a rational function because the top, again, is the equation of a line, and the bottom is a parabola, or x squared. In the denominator, our restriction is 0 because if we had 0 for x, 0 squared is 0, and again we'd be dividing by 0, which is a restriction. So both numerator and denominator are polynomials, therefore these are rational functions. A non-example would look like this. In the numerator, we have 1 plus x, which is polynomial. That's a degree 1 polynomial or equation of a line. In the denominator, we have the square root of 2 minus x. We do have a restriction that x can't be 2 because that would make the denominator 0, but our denominator is a root function, which is not a polynomial function. Therefore, this function f of x is not a rational function. So to summarize, rationals have to have numerator and denominator as polynomial functions. Since rational functions are quotients of two polynomials, they may possess discontinuities. Below are 4 common examples of discontinuities common to rational functions, and we'll discuss when they occur and why they occur. The first one is a hole. Holes occur in rational functions where the numerator and denominator, or the polynomial on the top and the polynomial on the bottom, have a common factor. To see if they have a common factor, we'd have to factor both numerator and denominator. So to start, how do we factor x squared minus 4? Well, that's a difference of squares. So we take the square root of the first term x, and that becomes the beginning of both of our brackets. And we take the square root of the last term 4, which is 2. That becomes the end of both of our brackets. And since it's a difference of squares, one bracket's plus, one bracket's minus. The bottom is already factored. And we do have a restriction in the denominator. The denominator, x cannot equal 2 because that would make the denominator equal 0. So where is our common factor? Well, our common factor is this x minus 2 term. We can divide it from both top and bottom. What that leaves us with is the equation x plus 2, restriction stays, x cannot equal 2. That restriction 2 is the hole. When we divide the hole away, it's removed from the equation, but it still remains as the restriction. The restriction 2 came from this bracket, which was divided away, because it was common to both top and bottom. At this value 2, we'll have a hole. So on our graph, at 2, we would have a hole at some y value. To figure out what the y value is, we would plug in 2 to our new equation of our rational function, which is f of x equals x plus 2. So to find our whole, we would say, what is f at 2? Well, that would be 2 plus 2, which is 4. We know x can't equal 2, but when it does, we have a whole at 4. This is the equation of a line, so our rational function will look like a line with a whole. This line has a slope of 1, a y-intercept of 2, so that means we're going to go through a point right there, and we're going to go through as a line. So let me grab a ruler here, and we'll draw a line. Not through our hole, but passing by our hole. And that's our first type of discontinuity, which is a simple hole. This equation of a line is a rational function, which has been simplified, and it's rational because we have a discontinuity, or a hole. The numerator and denominator were both polynomial functions, even after it's been reduced. The denominator would be 1, which still makes it fit the definition of numerator and denominator being polynomial functions. I don't white that back out because we don't need that. The second type of discontinuity is a vertical asymptote. Vertical asymptote occurs in a very similar way to a hole. We look at the restriction in the denominator, but in the case of a vertical asymptote, we don't have a common factor that divides away. So in this case, our top is x plus 1, our bottom is x minus 2. Notice that x minus 2 doesn't divide away this time like it did in our first example, so that hole remains. Our restriction is that x cannot equal 2, because 2 would make the denominator 0, and that's actually our vertical asymptote. To find your vertical asymptote, regardless of which polynomial you have, you always look at the denominator and set it equals to 0. So our denominator in this case is x minus 2, set it equal to 0 and solve. X equals 2 is the equation of the vertical asymptote. So f of x will have a vertical asymptote when the denominator's function is set equal to 0. And that a value, or whatever value makes it 0, in this case 2, is your vertical asymptote. So on our graph, at 2, we would have a vertical asymptote, which has the equation x equals 2. So holes, you look at the denominator, look for the restriction, and if it divides away, it's a hole. If it stays in the denominator, does not divide away, it becomes a vertical asymptote. Okay, that's 2 of our restrictions. Let's keep going. Our third type of restriction is a horizontal asymptote. Horizontal asymptotes occur in 2 cases. The first case is when the degree of the numerator is equal to the degree of the denominator. When the degree of the numerator is equal to the degree of the denominator, we have a horizontal asymptote. The reason why is, well, let's look. We know our horizontal asymptote will occur as x approaches infinity and as x approaches negative infinity. We want to know what f of x approaches. So let's think. As we get really, really large x values, what value would this function be approaching? Well, I'm going to mentally plug in the number 1,000 and see what this is approximately. This would say 2 times 1,000, which is 2,000, over 1,000 plus 1, which is 1,001. 2,000 divided by 1,001 is slightly less than 2. Okay? If we were to plug in a million, this would say 2 million over 1,000,001. 2 million divided by 1,000,001 is slightly less than 2. So what you see here is we're tending towards 2. An easy way to see that is to simplify this function by approximating. This is approximately, as x gets really big, the same as 2 over x plus x. We can ignore the plus 1 because that is a really small influence on the value of y when x gets really, 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 really big, like a billion. That plus 1 is going to impact the y value very, very small. or very, very small amount. Now we can simplify by dividing our x's, and we end up with approximately equal to 2. And that's actually the equation of the horizontal asymptote. As x approaches infinity, as x approaches negative infinity, f of x approaches 2. That's the equation of the horizontal asymptote. To simplify the explanation even more, let me grab my highlighter here, we're basically just looking at the ratio of the x values. So what's 2x divided by x? Or even just the ratio of the coefficients in front of x. So what's 2 divided by 1? Well, it's 2. That will always be the horizontal asymptote when the degrees are equal. We take the ratio of the coefficients on x. And in this case it's 2, so we would have a horizontal asymptote with the equation f of x equals 2. Our second scenario when we have a horizontal asymptote is when the degree of the denominator is larger. When the degree of the denominator is larger, our horizontal asymptote will still occur as x approaches infinity and as x approaches negative infinity. So that's really far to the right or really far to the left on the graph. Where's the graph leveling off to? In our first case, it was leveling off to 2. Sorry about that. As x approaches infinity or as x approaches negative infinity, what's happening to our graph? Well, as we plug in larger values of x, what's happening to the numerator and denominator? The example we just talked about was if we plug in 1,000, it'd be 2,000 over 1,000,001. If we plug in 1,000,000, we would have 2,000,000 over a number that would have 12 zeros, so a 1 with 12 zeros plus what, which is even bigger. And what happens is the bottom is getting bigger way faster than the top. When the bottom of a fraction gets really, really big and the top can't keep up, that number tends towards 0. And as you plug in larger values of x, you will see this function tending towards 0. And this will always happen when the degree of the denominator is larger than the degree of the numerator. It doesn't matter how much larger, so that this is a degree 1 over degree 2. A degree 1 over degree 5 would behave the same way. The denominator's degree is larger, the function will always tend towards 0, which means that you'll have a horizontal asymptote at f of x equals 0. And that will always be true when the degree of the denominator is larger. So the HA, or horizontal asymptote, will always be 0 when the degree of the denominator is larger than the degree of the numerator. So this leaves one scenario. One scenario that's left over is what happens when the degree of the numerator is larger than the degree of the denominator. Well, in this case, we have, I guess it's example 4 happens. In this case, we have something called an oblique or slant asymptote. An oblique or slant asymptote means we have an asymptote that looks like a line that has a certain slope. So it might look like a line like this, or it might look like a line like this. And the graph will behave around that as it does every other asymptote. It'll approach the asymptote and behave around it accordingly. It'll either approach from the bottom and continue to approach it as the asymptote goes down or up or whatever direction the asymptote's going. And we do our analysis the exact same way around an oblique asymptote as we would around a horizontal asymptote. What happens is x gets really, really large and positive or really, really large and negative. Does the function go up towards infinity? Does it go down towards negative infinity in the case of an oblique asymptote? So how do we figure out what the equation of the oblique asymptote is? Well, we actually do polynomial division. So if we have a rational function where the degree of the top is bigger than the degree of the bottom, this is a degree 2 over degree 1. we would do some polynomial division. We would do x plus 1 divided by, or divided into, x squared plus 4, and of course we need to insert a placeholder because we're missing our x term. And then we do our polynomial division. X plus 1 goes into x squared plus 0x x times, which leaves us with x squared plus 1x. If we subtract down the columns, we get negative x. Bring down the 4, we get plus 4. And now we're looking at negative 1 is how many times x plus 1 goes into negative x plus 4. Negative 1 times x is negative x. Negative 1 times 1 is negative 1. Subtract down the columns, and we end up with 5. When we write our division statement, we would say when we divide x squared plus 4 by x plus 1, we get x minus 1 plus our remainder 5 over x plus 1. And here we have two things. We have our first part is x minus 1. This is the equation of the oblique asymptote. And this part is the remaining rational function. The fact that there's a remainder tells you that we have a rational function. If we could divide this evenly with no remainder, all it would mean is that we have a whole. This x plus 1 is a factor of the numerator, and we would just have a whole. We wouldn't have an oblique asymptote. We'd have a whole, and our graph would be a line. But since we don't divide evenly, and we have a remainder, this tells us that we have a rational function left over with an oblique asymptote of x minus 1. What that means for our equation, well, minus 1 is the y-intercept, and the slope is 1, so that means we go through 1, 1, and our graph would look something like this. By graph, I mean asymptote. Our asymptote will look something like that. This is an oblique asymptote called f of x equals x minus 1. So you can have horizontal asymptotes, you can have vertical asymptotes, and wholes. And now I'm telling you, you can have something called an oblique asymptote, which is a line asymptote. That's when the degree of the numerator is 1 higher. We divide and get a line. What do you think would happen if the numerator was 2 degrees higher? In fact, what would happen if the degree of the numerator was 3 degrees higher? What do you think those asymptotes would look like? Think about that tonight, and we'll talk about it tomorrow in class. Thanks for watching.